Okay, so before we get to quaternions, I wanted to get you an overview of what we will be doing. I think following 2 or 3 lectures, depending how quick we go. And it's finally rigid body physics. So organizational things. So the Jello and cloth homework grades, I think, being released. Have you seen that? I think in general it was pretty good, especially the cloth. Your clothes look pretty good. Yeah, and we will be working on the fluid homeworks hopefully soon enough, so you will see that one too. Don't forget that 2 weeks from now, the 21st and 23rd of April, we have the final project demos. So make sure you have something to show for that, because it will be the 2 classes will be dedicated to you coming here and demoing what you have done for the final projects. Yeah?
So I think you probably already talked about it when you introduced the project, but what percentage of our grade is dependent on what we present in 2 weeks versus what we actually turn in like 2 weeks after that?
There's some percentage, right? Some percentage of the grade is the presentation. I forgot how much was it. Was it like 25, 75, some stuff like this. Oh, there is also the updated website. Not sure if you have seen it. We have finally updated it, I guess. It might even be written there.
So is the presentation grade mostly based on just the quality of the presentation, or on like the amount of technical stuff that we have implemented to that point?
Well, I mean, it's mostly the presentation, right? But it also matters what you are actually showing, right? So, all these things are intertwined. I cannot really tease them apart. I don't think it's here, but it is. Oh, the course schedule has been finally updated. Sorry that it took so long. So the final project slides are here. Behind. There we go. So you were wondering what is the... Yeah, 25. So that's right. So, and that's really mostly the presentation, right? Like some people, like last year, some people like went over time. That's not cool, right? You need to learn earlier in your career that's the last thing you want to do if you are presenting, be it a company or university. Like first thing you need to be is on time, and you need to deliver. You need to really explain clearly what you have done, right? How does it differ from what people have done before? What is your actual contribution there? Guess it's not the first time you guys are presenting something like that, right? Okay, any other questions regarding your final projects? I hope you are, if not already working, then at least starting to work on them. Okay, so today some people are working on rigid body physics, and that's what we will cover. That's one of the standard techniques, and we will get to quaternions in a second. I just wanted to explain you why do we want to care about these things. So rigid body physics is pretty standard by now. Like you know, pretty much all computer games now have some rigid body physics in them. And that's because this stuff is implemented in quite a few libraries, like PhysX or Havoc. Havoc is the standard one. There is ODE. Bullet is a good physics body, rigid body engine. Yeah?
Can you just lock the focus?
Oh, is it again? Hang on. Yep. Did it do that? Yeah. There are 2D rigid body physics engines. The Box 2D, I think that's what was used on Angry Birds. So physics. Rigid body physics is an important component of gameplay. That's, I guess, why it became so important, right? Because it really allowed game designers to do new gameplay elements, I don't know, kick the ball to get it somewhere, right? Rigid body physics is an essential component of that. So it's not just like an effect, which makes the game look cooler, like improved rendering or something like that, but something that can really let you play in new ways. And yeah. Physics is fun, right? You should have go to the point at this point of the course. And rigid bodies are probably the, I don't want to say the simplest thing to simulate, because there are quite a few tricky parts, but certainly from a computational standpoint, like the amount of compute you have to invest is pretty small, right? And why is that? It's because you can optimize the physics of rigid bodies, taking advantage of the fact that the object does not deform, right? So first you could object, why do I care about this? Isn't this just a special case of what we have covered before, of like, I could say, before we talked about volumetric elasticity, right, with FEM, or even just simple mass spring systems, you could say, well, why don't you just do this, right? So here is my rigid body. I take 4 particles, that's the 4th one, connect them in a tetrahedron. I can pick them whatever way I want, right? And I say that these are springs which are like super stiff, infinitely stiff if I want a perfect rigid body, right? And I simulate this using my mass spring system simulator, and I have a rigid body, right? I can attach what I want to this tetrahedron. I can embed like a bunny or whatever in there, and that's going to be my rigid body. That will never deform. Is the embedding thing clear? Do I need to comment on that, or do you know how would you? If I only simulate, actually maybe I should explain this. If I simulate like 4 points connected by infinitely stiff springs, I effectively simulate a rigid body, right? Now this is typically not what I want to render, just a tetrahedron, just at 4 points. I want to render some nice mesh, right? Something cool going on, like typically some boxes falling. Maybe you would want the box, right, to display, or a rock, or whatever is your rigid body. Barrel. So if I just want to attach it to the tetrahedron, all I would need to do is compute barycentric coordinates of all the vertices of my mesh with respect to these 4 points of the tetrahedron, and then just transform the fine vertices using barycentric interpolation. That's pretty basic thing. Okay, well, let me try to not digress too much. So, why don't we do this? What's the problem with that? You could just use your existing simulator for mass springs. Yep.
Is it more computationally expensive than just doing that, I guess?
Exactly, that's very true. And why is it more computational? What is the problem there? Like, the problem is these springs, right? They said infinitely stiff. That can be good, right?
Yeah.
Because even if they are not infinitely, even if they have just like finite but very high stiffness, so it like effectively looks like a rigid body, but it's not perfectly rigid. What that would mean that the forces in the simulation are insanely high, right? And you know that integrating something with very high forces, it requires you to do like implicit integration and maybe also choosing small time step. So numerically the problem becomes very difficult, right? So a much better idea is to basically make this conceptual. Don't really create like infinitely stiff things between the points on a rigid body, but abstract it away. Really say that this is just a rigid body, and figure out the laws of motion for a rigid body to begin with. Okay. So what are, if I'm talking about a rigid body, that means that's something that cannot deform. That's an abstraction, right? Such a thing does not exist in the real world, but it's a useful abstraction for our simulations. Now, how many degrees of freedom are in a rigid body motion? If I have some rigid object, like this pen would be fairly good rigid, except that it can like articulate like this. But if you imagine it doesn't, it can like float through space, right? And how many floats do I need to describe? Yes, exactly. 6 degrees of freedom, right? So what are they? So certainly there are 3 for translation, right? X, Y, Z coordinates for translation. And 3 for rotation, exactly. Ravich and yeah, exactly. The translation is fine, that's the linear component, and rotation, that's always the troublemaker, right? That's the nonlinear part. That's also why in the finite element methods, which we discussed previously, we had to play all these games with like the more complicated strain tensors to get around the nonlinearity. It turns out that if you represent it with 3 degrees of freedom, you will never get out of singularity. There is some sort of theorem which tells you that if you have a sphere, you cannot unfold it onto a plane without having to cut something somewhere. Okay, it's not a great way to explain this thing. But you need to add some additional degrees of freedom if you want to have a singularity-free representation. So the most common one is using a matrix, right? So I just take a matrix, which is a 3 by 3 matrix, and also happens to be SO3. Maybe I should write it like this. So 3 by 3 matrix. So the SO3, what does that mean? That means that the matrix has 9 degrees of freedom. It's a 3 by 3 matrix, right? And if this is to be in one-to-one correspondence with rotations, that means that this group has to remove 6 degrees of freedom, right? So where do they get removed? Do you know that? Exactly. So if I have the matrix, like I write it like this, M1, M2, and M3, those are basic things, but it's good to recap them before we go to quaternions, or to motivate quaternions, actually. So this like M1 would be a 3D vector, x, y, z, M2 would be also x, y, z, M3 would be also x, y, z. And we have, if this is to be orthonormal matrix, then we have these 3 constraints you mentioned, right? That M1 has to be orthogonal to M2, M1 has to be orthogonal to M3, and M1 has to be orthogonal to M3. So those are 3 constraints, right? It's so basic that I'm not even writing it down. I'm just like talking about it. What are the other 3? You have 9 degrees of freedom. Those are 3 constraints. So they take 3 degrees of freedom away, right? And there are still 3 more which we need to get out of it. So the matrix is not just orthogonal, but orthonormal. That's another thing which actually does not take out any degrees of freedom, interestingly enough. The thing is that if it's an orthonormal matrix, so MTM, if this is my M, really gives me identity. Yeah?
Each vector has length 1.
Exactly. So M1 has length 1, M2 has length 1, M3 has length 1. So those are the other 3 constraints. Yeah. And you are right, that also must be true that the determinant must be +1. But it turns out that from this, it already implies that the determinant of M must be plus or minus 1. So if you only restrict it to +1, you like cut the set in half, but then you don't reduce the number of degrees of freedom. Anyway, the point here is that if you represent rotations with rotation matrices, the special orthogonal group in 3 dimensions, you essentially are storing 9 floats, 9 scalars, and you impose 6 constraints on them. That's how you get back to these 3 degrees of freedom. Now this is a little bit wasteful, as you can imagine, and that's where quaternions come into play. That's what we will discuss right now, because quaternions are quite often used in rigid body physics for this reason, that they are more efficient, and also they are easier to normalize. I'll explain that when we talk about integration of rigid body physics. So quaternions have 4 degrees of freedom. So let me put it like here, quaternions. And SO3 meaning matrices, 9 degrees of freedom. And there are 6 constraints. And of course in quaternions there must be 1 constraint. If you have done graphics, if that's your background, then you have probably heard about quaternions, right? Who did? Oh, quite a few of you. So this will be, so some of that will be a recap, but maybe not completely because I have some some other things in my quaternion lecture. By the way, this quaternion part, oh, maybe I should say, so today we will cover the quaternions, and then we will go on to, if you want to do some reading on rigid body physics, there are these excellent tutorials written by David Barratt. They are sort of old, but the stuff hasn't changed really. This still applies. This is still the best tutorial you can do. There are also books on the topic, but I think that these tutorials are just good enough. And there are two parts to it, and we will cover both of them. Starting with quaternions. By the way, the seminal paper on quaternions is this one, Animating Rotation with Quaternion Curves at SIGGRAPH 1985. So I was already alive, but I wasn't very old then. This is the guy, Ken Shoemake, who actually introduced quaternions to computer graphics, and now they are used like pretty much everywhere. Like if you look at any game engine or something, it's usually using quaternions exactly for this reason, right? Because you only need 4 numbers as opposed to 9, and there's less constraints. So like things become easier, even though the mathematics can look a little bit more complicated. Computationally, it's more efficient. By the way, this guy was a PhD student here at Penn. But what happened to him, I have no idea. I lost track of him, even though he done this incredibly famous and influential paper. All right, so let's take a look at quaternions. So quaternions are a generalization of complex numbers, right? If I only did this, I could say it's a complex number because the I is a complex unit. And it's the same unit, the same algebraic thing, even in quaternions. Except that in quaternions we have 2 more. We have the J and K, right? So this is like a 4-tuple. You can also look at quaternion as a 4-dimensional vector. So how to add them and subtract them and multiply them by a scalar, that's trivial, right? I'm not gonna go into details on that, you should know that. The non-trivial thing is how to multiply them, right? And that's what makes an algebra, that we can multiply the objects together. And that's totally not trivial how you should multiply 4 tuples. There was this famous Irish mathematician, William Rowan Hamilton, who was struggling with this problem for a while and eventually got the brilliant idea that what he needs to do is to introduce a 3rd unit. Before he was thinking just about 2. And then he can get this symmetric multiplication rules, this beautiful rules for how the quaternion units should multiply. You can see that basically the idea is the same. J squared and K squared will also be -1, and they all together will also get you -1. And from this you can derive how what will be I times J, for example, right? Because all you need to do is multiply this from the right with K, and you will see that I times J will be K. You can also do it using this diagram, I, J, K, like this. So that tells you if you do I times J, you will get K. If you do J times I, you will get -K, and similarly for the other ones. So for example, J times K will be I, and so on. So this is how, those are some abstract numbers, just like the complex unit I, except that we have J and K, which have these multiplication rules. And they are defined for a reason. They are defined so that they satisfy certain algebraic properties. By the way, do you know what this is from? There is a story to this discovery, because when Hamilton finally figured this out, he just happened to be walking across a bridge in Dublin, and he was so excited that he carved these formulas on the stone of the bridge, and this is a memorial plaque which is still attached to the bridge. When I lived in Dublin, I made there a trip and took this picture. It's sort of ugly area. It's like there's like graffiti around that bridge, you know, sort of dodgy area, and somebody like tried to scratch the Hamilton name. I don't know why, but this is the Hamilton Bridge where the discovery was originally made. So there is a cool way to interpret quaternion multiplication geometrically, and also to interpret quaternions geometrically. So if I have 2 quaternions, Q0 and Q1, I can write their components like this. So the W0 is what we call sometimes the scalar or real part, and this would be the vector or purely quaternion part. That's the R0. So you can essentially think of it as a 3D vector, just like you can think about a quaternion as a 4D vector. And this is a decomposition into the real part and the purely imaginary part. And the nice thing about this splitting into the scalar and the vector is that then you can write quaternion multiplication using a dot product. This is a notation for dot product. This means dot product. Let me put it there. Dot product. And this is vector product, right? So the quaternion multiplication, these rules, these things from the bridge, and this diagram here, which you can derive from the formulas on the bridge, you can after some like rearranging things, you can distill this geometric expression out of that. So I'm looking at it now. This probably should not be cross product, right? This should probably just be a scalar product, because W1 is scalar. Now here there is a cross product, right? Yeah, I don't know what this did there. Yeah, so but the point is that it's mixing dot product and cross product, and some people like go even beyond quaternions to Clifford algebras, and they call it like wedge product, inner product, and outer product, and like it gets even more complicated. Let's stay with quaternions though. So the important property of quaternion multiplication is that it's associative. Do you remember what is associativity in algebra? That means that if I take 3 quaternions and I do Q0 times Q1 and the result times Q2, I'll get the exact same thing as if I do first Q0 and multiply it with Q1 and Q2. So I mean first multiply Q1 and Q2 and then with Q0. Now I have to be careful about the order because quaternion multiplication in general is not commutative. So that means that Q0 times Q1 does not always have to be Q1, Q0. Now it can be sometimes, but not always. Like for example, when they are both 1, then you can certainly, or just scalars, right? If all these are zeros, then you certainly can swap it, but you cannot swap it in general. And you can also think about a quaternion dot product. So this was like a dot product on 3D vectors, but you can also define dot product on 4D vectors, right? And you just say that W0, X0, Y0, and Z0 is just a 4D vector. And then you can think about a 4D dot product. And that's sometimes useful. So just like we have a bunch of operations with complex numbers, we have also some operations, basically analogous operations with quaternions, except that we need to be careful about the order of the multiplication. So there is quaternion conjugate, which is really just a generalization of complex conjugate, where we negate these purely quaternion components, the I, J, and K, they come with minus. And quaternion norm, again, just like complex norm, you do Q conjugate Q and square root. So the Q conjugate Q is just a scalar. The imaginary parts, they fall out. So the quaternion norm will be just a number. And particularly important is the set of unit quaternions. And unit means quaternions that have norm 1. That will be important because this is how we will represent 3D rotations. Okay. Now there are some properties of the norm of the conjugation. So it's true that if I multiply P and Q and take the norm, that's the same thing as first taking the norms and then multiplying the norms together. It's fairly easy to prove. You can prove it directly from quaternion multiplication. Same thing for the conjugation. So the conjugation sort of behaves like inverse of matrices. Because if I conjugate P and Q, that's the same thing as conjugating Q and P, but switching the order of the product. Right? So PQ conjugate is Q conjugate, P conjugate. Yeah, and if P is unit, that's one of the, P conjugate commutes with P. So if P is unit, that gives me exactly 1. So for a unit quaternion P, the conjugation gives me exactly the inverse, meaning that P conjugate times P is the same as P times P conjugate, and in both cases that's just 1. So that's basically the inverse unit quaternion. Okay. Yeah, I'm not going into too much detail because you have seen this before mostly. So there is Euler's identity for complex numbers, right? Let me write the complex numbers one, maybe here. You remember the Euler's identity for complex numbers? So it says that every complex number which is unit can be written like this: cosine alpha plus I sine alpha. That's for any unit complex number, right? You know this. It's a standard identity. You can prove it, for example, using Taylor's polynomial. Now, the analog of this formula works for quaternions, except that this R here, it's not going to be just I, like here, but it's going to be a vector, 3 degrees of freedom thing. So this R, you can look at it either as a vector or a quaternion with 0 scalar part. Okay, in both cases it's length 1 thing, and this will be essentially the coordinates of the axis of rotation where we tie it to a rotation. But you can also look at it just purely mathematically, that every unit quaternion can be written like this, and if it's not unit, then the only thing you need to do is put here the norm of the quaternion. Okay, so in general, any quaternion can be written in this sort of like polar way: the length times the exponential of R times alpha. Of course, for unit, this length of Q is 1, so that goes away. And why this is useful? This is useful for defining a power of quaternion, because then we can easily raise it to power of t, because then just multiply the angle, or which can either in the exponential form, it's here in the exponent, and in the cosine and sine, we just multiply the angle by t. So that's how you can define a power of a quaternion. Any questions here? Now here is the cool thing. Here is how quaternions relate exactly to 3D rotations. So rotation in 3D is characterized by an axis and an angle. And I think I should probably explain this a little bit better, why for a 3D rotation we have an axis of rotation. So actually before we go to quaternions, let me make some notes just on matrix representation of rotation. So the question is, why rotation in 3D has an axis? That's not so trivial, I believe. If you just think about, so what is a rotation? Rotation is a matrix, which is a 3x3 matrix, right? And is in SO3, right? So it's orthogonal and has determinant 1, right? So in particular, it means that RTR is RRT. That's the orthogonality. That's identity. And the determinant of R is 1. And what is axis of rotation? Well, axis of rotation has the property that's a vector such that the rotation maps it to itself, right? That's the static, that's the fixed subspace of this linear transformation. That's something where the rotation does not do anything, right? Everything sort of revolves around, but if I have the axis of rotation, it stays, the points there stay put, or the vectors in that direction stay unchanged, right? So do you know how can we prove that for every rotation there is an axis in 3D? So there is a cool way to prove it using a basic linear algebra. So what we can do is look at the eigenvectors of R. So what are eigenvectors? Well, those are vectors x such that Rx equals lambda x. Do you remember your linear algebra classes? So that so the standard linear algebra exercise you typically do is that you convert it to this, right? This is the condition for eigenvalues, and then you say that if lambda is an eigenvalue, that means that the determinant of m minus lambda I must be 0, right? And what is the determinant of m minus lambda I? Well, let me write it bigger. So this, oh wait, this was R. This is R11 minus lambda. This is R12, R13, R21, R22 minus lambda, R23, R31, R32, and R33 minus lambda, right? So if you think about what this is just a polynomial degree 3, right? So you can write this as a lambda cubed plus b lambda squared plus c lambda plus d. Where the a, b, and c are some coefficients depending on these r's, on the actual values of the matrix, right? Now, we know that every 3 by 3 matrix will have three, so if we, okay, let me do it properly. So if I'm solving for eigenvalues, I have to set this polynomial to 0, right? And we know from the fundamental theorem of algebra, I think that's how it's called, that there are 3 complex roots, right? There are 3 solutions, but they can in general be complex, right? Do you remember this? Now we know more than that. We know that these the eigenvalues come in complex conjugate pairs, right? If lambda is an eigenvalue, then it means that lambda complex conjugate is also an eigenvalue. Right. So in case I have 3, this guarantees that at least one of them must be real, right? Right, one of them is going to be a real number and the other 2 will be complex conjugates of each other. And now take a look at this. So if I have some vector x transformed by the matrix, so what is the squared norm of this? That's the xt RTR x, but I know that RTR is identity, right? So this is just the norm of x squared, right? But if Rx equals lambda x, so if my lambda is an eigenvalue, so this is also equivalent to the norm of lambda x squared, which is lambda squared times the norm of x squared, right? So I see from this that lambda squared, norm, let me write it again, norm x squared, I can divide it by norm x squared, I will see that lambda squared is 1, which means that lambda can be only plus or minus 1. That's for the real eigenvalue lambda. Okay, so this let's assume this lambda is the real eigenvalue. So it can only be plus or minus 1. So let's be concrete and let's assume that the lambda 1 is the real one. So lambda 1 is real. And then I know that the lambda 2 is something, and then lambda 3 must be lambda 2 complex conjugate, right? That means that lambda 1 is its own complex conjugate. It means that lambda 1 is lambda 1 conjugate. That's basically equivalent to saying that it's real. And then I have this complex conjugate pair lambda 2 and lambda 3. Now I have also this condition that the determinant of R is 1. And the determinant is equivalent, so 1 is the determinant of R, and the determinant is equivalent to the product of eigenvalues. So that's lambda 1, lambda 2, and lambda 3, right? So I just explained that lambda 3 is the complex conjugate of lambda 2, so this means this is the square norm of lambda 2. Because lambda 3 is complex conjugate of lambda 2, I have a complex number times its conjugate, which is the complex norm. And that means if this is plus positive 1, this is also a positive number. So that means that lambda 1 also must be positive. So that leaves only the option that lambda 1 is plus 1. And if I found an eigenvalue which is plus 1, well, that means that the associated eigenvector to this eigenvalue, the x corresponding to the eigenvalue lambda 1, has the property that Rx equals x. And that's exactly what I need. That's my axis of rotation. Okay, I know I went a little bit too fast because there is like some things from linear algebra and so on, but I don't want to spend the whole lecture just on this. I just wanted to show you that for every rotation matrix, there is an axis of rotation. There is a vector which the rotation leaves alone. And what this is also how you can find, by the way, an axis of rotation, right? You can find the eigenvector of the matrix R, which corresponds to eigenvalue 1. That's the axis of rotation. And you could also be asking the question, what is the R matrix doing in the orthogonal directions to the axis of rotation? And in the orthogonal directions, what do you think is there? So if I draw it, if this is my axis of rotation A, and I pick some two orthogonal directions, say B and C, what do you think the matrix R is doing in the linear subspace generated by B and C? Or did I completely lose you? Hope not. So the components of any vector in direction A, the R matrix is leaving alone, right? And what is happening to the component in the B and C plane? I mean, if I take any vector, say P, you can decompose it into a component in the A direction and here in the BC direction, right? So the component in the A direction stays put, because that's this, right? What happens to the component in the BC plane? It's very simple. You can just guess. Don't be shy.
Saying it rotates too simple.
Yep.
No,
That's all it is. It rotates. It's a 2D rotation.
Yeah.
Right? It's a 2D rotation in the plane generated by B and C. So 3D rotation is really nothing but an axis of rotation which points somewhere, and in that direction nothing is happening, and a 2D rotation in a plane where we actually are doing some rotation. That's all that 3D rotation is. And linear algebra makes this not hand wavy, this argument. that's the whole point of this. Yep.
So it's you have a vector, right? And the rotation, the scalar is the rotation angle along this vector, right?
The what?
It's the rotation angle around this vector, right?
What is the rotation
The
angle?
scalar component of the rotation angle.
Sorry, I can't hear.
The scalar component is the rotation angle.
Which scalar component?
Well, you said that you can represent the rotation as a vector of rotation and then scalar, like an angle.
Right. Axis of rotation and the angle of rotation. Yeah. So
Is this the angle like around this vector sort of?
So the angle, yeah, that's a good question. So here, the axis of rotation, how the length of the axis of rotation doesn't matter, right? You typically pick this A vector to be unit. Because of course, if you scale it by something, if I scale it by alpha, then guess what I will get? Well, alpha A, right? It's just an invariant subspace, one-dimensional inner subspace, if I want to be like really precise, right? So where is the angle of rotation? Well, the angle of rotation lives in the BC plane, right? That in the BC plane, this transformation is a 2D rotation.
Yep. But then where exactly is, like, let's say 0 angle, 0 degrees angle, and where is like 180 degrees angle? Where does it start? So let's say, like, is there a way to know?
For if you have 0 on 180 degrees, then the axis of rotation is not uniquely determined. You're right that this is actually what you have found, and that's a very good observation. That's the singularity of the axis angle representation. So one way to represent, so that's a very good point. So I told you that just using 3 degrees of freedom, you will always have problems, right? And some people, sometimes you can represent rotation just as a scaled rotation axis, right? Where you can say that A is your axis of rotation, and you say that the length of A is 1, so it's a unit vector, right? And you can scale it by alpha. That's the angle of rotation. So, okay, I'll write it here. A axis of rotation, and alpha is angle of rotation. So this way I would get 3 degrees of freedom representation of a rotation, right? But the problem is that as the rotation approaches to identity, that means that the alpha goes to 0, right? Because my angle of rotation goes to 0 as the rotation goes back to identity. And the closer I am to 0, the less determined is the axis of rotation, right? And ultimately when I'm at 0, I have to divide by 0 to recover the axis of rotation, so clearly there is something funny going on. Well, the thing is that there you have a singularity at identity. So the conclusion is that these problems go away if you represent rotations using quaternions, and that's what I will finally describe here. So all this discussion was just to convince you that for every 3D rotation there is an axis of rotation and also an angle of rotation. I told you how to find the axis of rotation. You find the eigenvector of the rotation matrix corresponding to eigenvalue 1. How to find the angle of rotation I did not cover. You would have to look at the 2D component and extract the angle of rotation from it. We will have an easier way how to find an axis and angle of rotation using quaternions in a little bit. So I will just do that. It turns out actually that computing with quaternions is usually it's easier than working with axis and angle directly. But it's good to note that the quaternion is actually not that far from axis and angle representation, because quaternion representation of a rotation uses A, that's the axis of rotation, and this is the angle. So if I want a quaternion corresponding to rotation about an axis A with angle alpha, then this is my quaternion. I take cosine alpha half, that's the scalar part of the quaternion, and here is the unit axis of rotation and times sinus alpha half, that's a scalar. That defines a perfectly valid unit quaternion. Because this vector is unit, you can easily prove that this whole quaternion is unit. And this quaternion really acts as a 3D rotation, which is sort of cool. So here is how quaternions tie to 3D rotations. Before, like, you could think of quaternions as some sort of weirdo generalization of complex numbers, right? But here is like their real impact to like computer graphics. So here is how it works. So if I take an arbitrary vector in 3D space, I can define a purely imaginary quaternion V, such that I put the coordinates of the vector as their I, J, and oops. There's so many mistakes there, sorry. This is supposed to be k, of course, components, right? In other words, I represent this vector as a quaternion with 0 scalar part. And then I do this. Then I compute q times v times q conjugate. This times means quaternion product, quaternion multiplication, right? This is a special type of quaternion which has 0 scalar part, and the q is also a little bit special because it's a unit quaternion. And what do I get from this is quaternion v prime. And believe it or not, the v prime will surprisingly also have 0 scalar part. Again, you can directly prove it by writing out the quaternion multiplication. If you want to do lots of homeworks, you can just prove all these things. So the scalar part is 0, and what are the non-zero parts? Well, those are the x1 prime, x2 prime, and x3 prime. So I did this quaternion product, 2 quaternion products, right? Q times v times q conjugate. And what I got out of it was 0, x1 prime, x2 prime, x3 prime. And interestingly, if you look at what is the x1 prime, x2 prime, and x3 prime, you'll find out that this is nothing but a rotation of x about axis A with angle alpha. So this is sometimes called the sandwiching product, because it's sandwiching the v between q and q conjugate. And that just realizes 3D rotation. So any 3D rotation can be described as an axis and angle, right? Even if the angle is 0, that's totally fine. By the way, what do we get for angle 0? We had troubles in the axis times angle representation, right? What do we get here if we have an identity rotation, 0 angle, arbitrary axis? Yep, just 1. And a very important thing to keep in mind, that this is something that's not always explained well in like books about quaternions and so on, is that this correspondence between rotations and unit quaternions is actually not unique. This is an important difference between unit quaternions and the 3D matrices, the rotation matrices, or if you will, between the group of unit quaternions and the group SO3. This is I think the main point I wanted to make in this lecture, so you remember this, because if you are coding it, this can lead to some pretty big errors, and you are like surprised, what is it coming from? Shouldn't quaternions be just like a different representation of rotations? Well, they should, but they are not exactly the same. There is this catch, which is called the double cover property of quaternions. Did you hear about that? See, that's what I thought. So the catch is that both quaternions q and minus q, they realize the exact same rotation, right? They're going to be pretty different quaternions, right? Think about identity, right? If identity is 1, so I'm saying you that if we take minus 1, that's like a very different number, right? Then the action of it when applied in the sandwiching product is going to be the same. Well, that's because the scalar multiplication commutes, unlike quaternion multiplication. So I can just take the minus 1s out of it. So I see that minus q v minus q conjugate is exactly the same as q v q conjugate. So it doesn't matter if I use q or minus q. Both of these quaternions will realize the exact same rotation. And this has important implications, which I'll explain in a second. First, let me do the basic things. So like if here is the exposing the relationship between quaternion, multiplication, and composition of rotations. So if I rotate it, this was here. So this means that I first rotated v by q, and let's say now I rotate it by p. Well, what do I get? So v prime was already v rotated by q, right? So I get pq v q conjugate p conjugate. And remember this property of multiplication and conjugation. This is q conjugate p conjugate is pq conjugate, right? So if I first apply one rotation and then another rotation, then it's equivalent to just saying, well, let's first multiply P and Q and then use that to transform V, right? So this really says that multiplication of unit quaternions exactly corresponds to composition of rotations. Now the second line here is for the special case that P is exactly Q conjugate. If P happens to be the conjugate of Q, well, then what happens is Q conjugate Q will give me 1, and the same here. So I will get back to my original V. So that means that that means the geometric meaning of conjugation of unit quaternion is inverse rotation. So indeed, conjugation of a unit quaternion is gives me exactly the inverse rotation. And it's of course trivial to see that 1 is identity, 0 angle rotation. Of course, if I multiply it with 1, and the conjugate of 1 is also 1, so if I just multiply with 1 from both sides, I'm not doing anything to it, right? So it just stays where it is. So that's what identity rotation does. Okay? Any questions? Here is how you can convert quaternion to rotation matrix. It would let me. Yeah, this is the formula. You could derive it again by writing out the quaternion multiplication. And this is basically how you can convert from a unit quaternion to a rotation matrix. So this is a 3x3 matrix, such that that R times X is equivalent to QX Q conjugate. That this matrix is realizing the same rotation as this quaternion. Now the opposite conversion from matrix to quaternion, you essentially need to invert this relationship. You are given the elements of this matrix and you need to figure out the X, Y, W, and Z's, right? So that's basically just inverting these formulas. It's relatively simple. The only thing you need to take care of is not to divide by 0, because each of these elements can potentially be 0, so you need to check which one of them is the biggest and make sure not to divide by the smallest one, but by the biggest one, and you'll be fine. This is fairly standard thing, like in most graphics packages, this would already be implemented for you, the conversion. Now here is the one application of quaternions which is not directly related to physics, but it will nicely explain you the double cover catch of quaternions. And will also give us some intuition about how quaternions then relate to rigid body kinematics, which is what we'll be studying next. So the interpolation problem, have you heard about spherical linear interpolation? Probably yes, right? If you had some graphics class, most of you did, some of you didn't. So the task is to find nice interpolation between two rotations. So I have two rotations, R0 and R1 as input, and I want to interpolate between them. So what does it mean? Interpolate. Well, that means I need to find a set of or curve of rotations parameterized by this t parameter, interpolation parameter, such that it starts at R0, ends at R1. For every t, it produces a valid rotation. And ideally, I would also want the angular velocity of an object transformed by RT to be constant. So that means I want a uniform interpolation, right? If I want to go from here to here, I want to go with constant velocity. Not like it first goes a little faster and then it goes slow. That's sort of like the most basic interpolation of rotations you can think about. So the first thing you could do, and sometimes you can get away with it, is to just do linear interpolation of rotation matrices. You probably know what problems does that have, right? What problems does that have? If I just take R0 and R1, represented as matrices, blend them together linearly, that means, of course, 1 minus t R0 plus t R1. What will that give me? What's the problem with that? You should know that thing. Yeah? not a rotation matrix anymore, exactly. So it violates this. So what is it if not rotation? What happens? Exactly. So like if I interpolate from here to here, then it doesn't really rotate, but it, okay, let me from here to here, if I want to interpolate from here to here, I should be really rotating this arrow, right? But what the linear path does, well, it just cuts the corner. So like the t 0.5 will be like here, right? So shortens things, not a rotation anymore. Now with quaternions, we can do this interpolation, which is sort of cool. We can just represent these rotations using unit quaternions. You can just convert the matrix to a quaternion, and then just interpolate the quaternions linearly and normalize. If we did not normalize, we would have a similar problem as before. It would not be a rotation. It would have some uniform scaling. If we normalize, we make sure this is a unit quaternion, and unit quaternion always represents a rotation. Okay? So this satisfies all of these conditions except for the last one. And I would like you to get the geometric picture of why this goes wrong. So unit quaternion. So let me first explain about unit quaternions. Maybe here. So unit quaternions are essentially four tuples, x, y, z, w, or the other way around, such that x squared, y squared, z squared, w squared equals 1, right? So the set of unit, could also denote it like q1. So all unit quaternions are geometrically this, right? What does it mean geometrically? What sort of manifold is that? What if I did this thing? What if I said it's only 2 dimensions? So what if I said this? No, what is this one? That's simple. That's now I'm in a plane and I have x and y coordinates, and I have this condition that x squared plus y squared must be 1. It's just, yeah, exactly. It's just a circle, right? Now if I go to 3D and I say I want x squared, y squared plus z squared to be 1, what is that? That's a sphere, right? And unit quaternions, that's one step above. That's a hypersphere. It means it's a 3-dimensional sphere existing in 4 dimensions. Those are the 4 dimensions. This is the 1 degree of freedom which is removed, and that defines a hypersphere. So you can think about it basically like extrapolate yourselves. Extrapolate the step from unit circle to unit sphere to hyperunit sphere. Now, of course, imagining hyperunit sphere I haven't succeeded in yet, and that's not the point. But what we can see, we can use it to get an intuition about this linear interpolation of quaternions. Because if I have Q0 and Q1, they are points somewhere on this unit hypersphere, right? Whatever this hypersphere is, right? But if I am interpolating between them, that means I go on the line connecting Q0 and Q1, right? Now this line connecting Q0 and Q1, if I also go through 0 and I put a plane through 0, Q0 and Q1, that cuts a plane out of the hypersphere, right? And in this plane, this plane I can already draw. If I project the hypersphere on a plane passing through the origin, I will get just a regular circle, right? So to analyze this, all I need to do is think about just a regular circle, right? So if my Q0 is here and my Q1 is here, then what this interpolation does, well, it essentially cuts through the straight line. There's the curved manifold, there is the circle, or which is a piece of the hypersphere, and this interpolation just goes on a straight line. And then what this division does, the division by the length, that's projecting it back onto the circle. And from this, it's sort of easy to see that the speed is not going to be constant, right? Because if I'm going with the constant speed on this line, that means I'm not going with constant speed on the circular arc, right? The nice thing is that this is actually not that big of a problem usually, because the difference between linearly going here, between uniform sampling here and uniform sampling here is not that big. So usually you can get away just with this linear interpolation of quaternions, which in theory violates the condition 4, but in practice, in graphics or physics-based animation, you usually will not notice. Now, if you want to be a real purist, then you need to do spherical linear interpolation. Let me just explain that quickly. Spherical linear interpolation. Basically, what spherical linear interpolation means go do uniform sampling on the spherical arc on quaternions. That's all it is, right? Instead of being uniform on the straight line between Q0 and Q1, you are uniform on the circular arc, right? So essentially what you need to do is to get this angle and then linearly interpolate the angle as opposed to linearly interpolating these two guys directly. And the way how we can write this in quaternion language is by doing this. So we say that the interpolant is P times P conjugate Q to the power of T. So the power of a quaternion sounds like fancy or whatever, but all that really is means linearly interpolate the angle, right? That's what the formula for the power was saying right here. All the power means is just the T gets multiplied with the angle. So that's exactly what we are after. So that's the famous spherical linear interpolation. I think it was also keyed by Shoemake in this famous 1985 SIGGRAPH paper. And that satisfies all of the 4 conditions. Now, in most applications, you can really get away with this linear interpolation of quaternions. You will not have exactly constant angular velocity, but like the problems are usually minimal. Now, where can be big problems is the double cover property. So let me explain that to you. Remember, I said that minus Q represents the exact same rotation as Q, right? Unfortunately, if we use minus Q instead of Q in interpolation, the results will be drastically different. So let's think about it. Why? So the scalar part of P conjugate Q, that's what we are computing here. By the way, what is P conjugate Q? Maybe I should spend a minute thinking about the geometric interpretation of that, right? So I have 2 rotations, P and Q. Here is how the slurp works. Maybe I should have explained the terms. What means the P conjugate Q in English? Well, what if P was identity, right? P could as well be identity. Why not? I can be interpolating from identity. Well, if P is identity, then what we are doing here, just exponential of Q, right? If P is identity, then the P just goes away, right? And if P is not identity, then essentially the role of this is to rotate this whole thing back, so you could imagine P was at the identity. So P conjugate Q, or this way. So if P is not identity, if P is general P, but T is 1, well, then I'm getting Q, right? I must be getting Q because that's the end of my interpolation, right? Because P times P conjugate is 1, right? So what does that mean? What is P conjugate Q? That's the relative rotation between P and Q, right? In matrices, if I had like a matrix MP and matrix MQ, if I wanted to compute so let's assume like the matrix MP rotates me somewhere, the matrix MQ rotates me somewhere else, but maybe where they rotate me is not that far. So if I'm interested in the difference, all I need to compute is MP inverse MQ, right? That gives me the relative rotation between MP and MQ. This is the same thing in quaternions, the relative rotation between P and Q. Okay, so what's the scalar part of this relative rotation? Well, we have in one of these formulas, my formulas here, if I had Q0 times Q1, then this is the scalar part, and this is the vector part, right? So if I'm giving is P and Q, and if one of them is conjugated, that means that this vector will be negated, and I will get just WPWQ plus the dot product of RP and RQ. Now don't be confused. This is just this is just the dot product. For some reason I chose to denote this dot product like this. Now we can look if we look at the quaternions as 4D vectors, we can take the dot product of quaternions. So this is a 4D dot product. This was a 3D dot product. This is a 4D dot product. And because they are unit, then the dot product is directly cosine of the angle between them. So you can think about, again, 4D vectors, maybe you don't want to think about them directly, but you know how 3D vectors work, so you can extrapolate your knowledge from there. So between every two 3D vectors, there is some angle, right? There is some angle sigma, which goes between 0 to pi, or 0 to 180 if your degrees are radians. So even between 4D vectors, I can measure the angle, right? Between any dimension vectors, you can measure the angle. And the dot product is the cosine of the angle sigma, okay? And the angle of rotation of the relative transformation P conjugate Q, that is 2 sigma, right? Maybe I should have emphasized that here. Notice this trick. You might have not paid attention to this divide by half, but this divide by half is actually quite important, because the angle in the quaternion is half of the angle of rotation. So if I want a quaternion which does rotation by angle alpha, then I have to divide the alpha by half when putting it into quaternion. That's essentially because you are sort of applying it twice, once from the left, once from the right. So then you're like doing like half rotation intuitively, right? So if I look at this relative transformation between P and Q as a rotation, it rotates about 2 sigma, okay? And what does that mean? That means if instead of Q I apply minus Q, then of course my dot product becomes minus P times Q. So if P dot Q was cosine sigma, then minus P dot Q will be minus cosine sigma. Using the trigonometric identities, I can write it as cosine of pi minus sigma. That means that the angle of rotation of this minus P conjugate Q is 2 pi minus 2 sigma. So for example, if my sigma was 60 degrees, that means I had a 120 degrees rotation. Then if I use minus Q, leading to the relative transformation minus P conjugate Q, then I will be getting 240 degrees rotation. So there is a huge difference between picking Q and minus Q. One of them will give me this short arc interpolation, and the other one will give me a long arc interpolation. So I certainly want to pick the one that leads to shorter arc interpolation, right? Interpolating it like this is probably not what you want in most applications. And how to do that is relatively simple. If you look at the quaternion picture, here is the quaternion picture. So this is again my hypersphere of unit quaternions sliced by a 2D plane, so I can actually draw it there, right? Imagine this paper is the 2D plane, which is passing through 0 and slicing the hypersphere at a circle, right? At any plane slices at a circle. And if my first rotation P is here, and q is here, then minus q, well, that's just a line passing through 0, right? The minus q is sometimes it's called antipodal point. Like you can look for every point on a sphere, where is the antipodal point. The other day I put like GPS coordinates like wrong. I wanted to go somewhere in Pennsylvania and I got it like with minus. So I think I got the antipodal point on the Earth, and I got somewhere to Kyrgyzstan or something like that. Fortunately, I did not go there. So that's what the minus does. And if you are interpolating between P and Q, then you are moving here. Then this is your interpolation. Like slurp would be going this way, right? Slurp between P and minus Q would be traveling like this. Right? So this corresponds, this shorter arc, because here the distances are twice compressed compared to the rotation space, right? Because here the angles of rotation we need to multiply by 2. So this, how do I squeeze both of them here? So going between P and Q corresponds to this shorter arc rotation, rotating the tree this way, and going between P and minus Q, that corresponds to this longer arc rotation. So obviously, if you want the shortest path interpolation, then we need to make sure that the dot product between P and Q is non-negative. And if it happens to be negative, then what we can simply flip it to the other Q, right? If somebody gave us minus Q, you don't really know if you have Q or minus Q, just get a quaternion, you don't know which one it is. Well, what you do, you compute the dot product. If the dot product is negative, you flip it. And that way you guarantee you have the short arc interpolation, right? By the way, the linear quaternion interpolation, that would be cutting through the straight line here, right? And would be uniformly sampling this line here. But then the normalization would be projecting it back here. From this, you can sort of see that the error is not going to be huge, right? Of course, if you wanted to be interpolating like here, that error would become big. But the thing is that already here, you have 90-degree angle here, you have 180 degrees rotation, relative rotation, right? And that's as much as you typically need to interpolate, right? Because if you needed to interpolate 200 degrees worth of rotation, well, then you just go the other way around, right? So, I mean, if my, yeah, again, that's the same situation, right? If my Q was here, then what do I do? Well, I project it here, and here I have less than 180 degrees. I mean, so if I, let me do it properly, if this was some R, and somebody wanted me to interpolate between P and R, that would be a rotation of more than 180 degrees. What I can do, I can take minus R, which will be here, and here all of a sudden I have an angle of rotation less than 90 degrees, less than 180 degrees worth of rotation. Sorry, angle between quaternions less than 90 degrees, which means angle of rotation less than 180 degrees. Okay. So that's about quaternions. Any questions regarding that? And by the way, this picture, keep this picture in mind, because this is sort of the useful geometry picture. You can have the exact same sort of intuition about rotation matrices, right? The point is that either in quaternions or in rotation matrices, we are in some manifold which exists which is embedded in a higher dimensional Euclidean space. So in the case of quaternions, maybe I can go back here, we are working on a 3-dimensional manifold. So 4 minus 1 is 3, right? 9 minus 6 is also 3. So in quaternions, we are working on a 3-dimensional manifold embedded in 4-dimensional Euclidean space. That's the hypersphere I was talking about. And on SO3, you can have exactly the same intuition, except that now our 3-dimensional manifold is embedded in a 9-dimensional Euclidean space. But again, locally, it means that you have some sort of curved manifold existing in 9D space. And when we will be working with rigid body kinematics, that means that if the body is to remain rigid, That means it needs to stay on the manifold, right? It needs to stay on this surface. It needs to be somewhere here. It cannot go like here, right? That's why when we cut through, we need to project it back. Because outside of here, there are not rotations. Rotations live only here, right? The funny thing about the quaternions is that the rotations essentially wrap around twice, right? Because imagine, okay, I'll do it. This is a sort of cool thing. So let me draw the quaternion circle again. This is 0, and let's say that this is identity. So this is rotation about 0 with 0 angle. Now if I travel like this, here I have rotation by how many degrees? Right here, 180 degrees, right? This is a 90 degrees in quaternions corresponding to 180 degrees worth of rotation. So I travel like here I do 180 degrees turn. If I continue traveling here, what turn did I do? 360, yeah. So that means I did like one full revolution, right? Like 180 and back to 360, right? So I am back. So this is -1. So it's a different quaternion, but the same rotation. That's the catch of this double cover property. That's why it's called double cover, because every rotation is represented by 2 quaternions. Now if I continue rotating, then this gives me 360 plus 180, whatever that is. And then if I continue back here, then I have done a full 720 degrees rotation, right? So I do like 360 and again. So if I do this to my bottle, that means I went exactly once around the quaternion hypersphere, or at least about the slice of my quaternion hypersphere. I have done this motion. Right? And this funny thing that every rotation is represented twice. This has interesting implications in the real world, believe it or not, because there is sometimes a difference between an object and the object rotated by 360 degrees. There is a cool thing called Dirac belt trick. If somebody has a belt, I can demonstrate. I unfortunately don't have a belt because this is attached.
This will work.
Do we still have time? Yeah, we still have 2 minutes, so I can show you the direct belt trick. This via SVR here, it sort of makes sense. I don't want to start the physics because no way we would finish it in time. Okay, so you can. Okay, I'll actually help you hold this for me. So I will be like concerned about rotation along the length of the belt. So let's say this is identity rotation, and I'm looking at the rotation here, right? So right now I rotated it, so let's see. So this is rotated by 180, this is rotated by 360, right? And there is some interpolation of the rotation along the length of the belt, right? This is interpolating from 0 to 360, right? Now I can do whatever I want with this belt. I can be messing with it. I'm keeping the orientation here and here fixed. I can be doing whatever I want with it, but this interpolation, I mean, I can change the distribution, right? I can like squish it all here, right? But that's about all I can do. I can get rid of it by like cleverly moving it around. But if I go again to 720, so now I think I went to 720. Again, I can sort of also redistribute it. But there is a cool thing I can do. And notice that I'm not changing the orientation of this, right? I removed the rotation completely. This is called Dirac's belt trick. What does it mean on quaternions? So the belt, if the belt starts here, and goes, I need to finish it quickly, and goes here, then I can distribute the rotation according to any curve on the quaternion hypersphere, right? But if I'm keeping this fixed, there's no way I can undo this. But if I go all the way around, then there is a funny transformation which essentially just makes the curve disappear. This has to be a closed curve. So if the curve goes 720, that I can just redistribute, move the curve continuously along, that it just vanishes and goes back to identity. And all the rotations all of a sudden disappear and become identity. So that's the fun with quaternions. Okay, thank you.